Olá, gente. Bem-vindos para todos. Bem-vindos para todos. Também a nova chefa do departamento, Arlene, vi ela entrar. Hoje temos a honra e o prazer de ter como palestrante a Zahra. Zahra é originariamente do Irã. Fiz graduação na Zahra University, e o mestrado no Sharif University of Technology. E depois fiz um doutorado junto entre o Instituto das Ciências Fundamentais no Irã e a Unicamp, com supervisão de Orlando. Depois ela fez pós-docs na USP, na Unicamp, e agora ela é pós-doc na Virginia Tech University. Como sempre, por favor, escreva, se você é estudante, precisa de reconhecimento que você está aqui, escreva seu nome e array no chat. Isso não vai ser parte do recording. Ela vai falar e depois vamos ter, se você tem uma pergunta urgente, pode escrever no chat, mas seria melhor deixar as perguntas até o fim. And without further ado, Zahra, please start.
Hi, thanks for inviting me to give this seminar. Today I will talk about precision measurements we can do at the DUNE Near Detector. The talk will be mainly based on these 4 papers. So every time I mention one of the papers, I will introduce the collaborators there. I will first talk about the neutrino Trident production at the DUNE detector and several other experiments that we have considered. Then I will discuss the scattering of neutrinos from an electron. I will use the information from these 2 neutrino interactions to extract information about the weak mixing angle, and also to put some constraint on some model-dependent and model-independent new physics. For the model-dependent, I will focus on some specific Z-prime scenarios, and for the model-independent ones, again, using the DUNE data, I will derive constraints on the parameters of an effective filtering formalism. So, as you all know, neutrinos at the standard model appear at the charge and neutral current interactions. Opposite to the other particles, we don't have right-handed neutrinos. Therefore, we don't have specifically a neutrino mass term in the Lagrangian. And so the standard model Lagrangian predicts neutrinos to be massless. However, after more than 2 decades of neutrino experiments, we know that neutrinos oscillate. And in order to explain this oscillation, neutrinos have to be massive and they have to mix. What does this mass and mixing of neutrinos mean, and what does it have to do with oscillation? We know that the flavor eigenstates of neutrinos, which are the neutrino which couple to charged leptons, the electron neutrino, muon neutrino, and tau neutrino, they are not the same as the eigenstates of the Hamiltonian nu1, nu2, and nu3. So the one which have specific masses are nu1, nu2, and nu3, and the one which are the flavor eigenstates are nu-e, nu-mu, and nu-tau. But they do not coincide. They are related through a 3x3 unitary matrix, the PMNS matrix, which it has 3 mixing angles and 1 CP violating phase. But they are not coinciding, and they are related through the parameters of this unitary matrix. And then the oscillation formula of neutrinos, which is saying after a distance L from the source, what is the probability of a neutrino with flavor alpha converting to a neutrino with flavor beta? It's given by the parameters of this matrix, which are the mixing angles and CP phase in these U elements here, as well as the mass square difference in the sine square and sine. So using this and using several different neutrino experiments, we can extract information over the parameters of this matrix, as well as this delta m squared kj, which is the difference between the square of the masses. So we already know a lot of information over these parameters. What we know is the value of the mixing parameters. So we know theta 1, 2, theta 2, 3, and theta 1, 3 very well. We also know delta m squared 2, 1, which is the solar mass squared difference very well. But for example, we don't know the sign of delta m squared 3, 1. So we don't know that if delta m squared 3, 1 is positive or whether it's negative. So in the neutrino literature, that's the so-called normal mass hierarchy. We don't know if we have a normal ordering, that is when this is with a positive sign, or if we have an inverted ordering, which is this is with a negative sign. We also don't know the value of the CP phase. There has been many experiments which are trying to measure that, but we don't still have a measurement. So although there are many things we know about neutrinos, there are a lot more things that we don't know. We don't know what's the order of neutrino masses. So we don't know which neutrino is the lightest one and which one is the heaviest one. We don't know what's the value of the CP phase. We don't know if neutrinos are Dirac or Majorana particles. We also don't know what's the mechanism behind the masses of neutrinos. We don't know if it's the same Higgs mechanism or if we have a separate mechanism which is giving mass to neutrinos. And most importantly, we don't even know what's the masses of neutrinos. We know the value of the difference of the square of the masses, but we don't know what's the absolute value of the masses. We also don't know how many neutrinos we have. We know that there are 3 neutrinos which couple to the Z boson, so we have 3 active neutrinos, but we could also have sterile neutrinos. So in order to answer several of these questions, we need some baseline neutrino experiments, which, for example, DUNE experiment is one of these examples which try to answer a lot of these questions. So the DUNE experiment is composed of a near detector and a far detector. So the experiment is designed like this. The near detector is located at Fermilab. We have a beam of protons which have an energy of 120 GeV and a power of 1.2 megawatt. This beam of protons hit a target of carbons, and then after hitting the target, it can produce some charge and neutral mesons. So the pions which are produced from this can decay to neutrinos, and also they can decay to muons, and then these muons can also later decay to neutrinos. We have a near detector which is almost 500 meters from the source, from the target. It's 574 meters from the source. And we have a far detector at Sanford Lab, which is almost 1,300 kilometers from the source. The place that is going to be built to study the CP phase and the mass hierarchy of neutrinos is this far detector. That's the distance we need for neutrinos to oscillate. However, we also need a near detector in order to study the systematic uncertainties. So we don't expect to see any oscillation at the near detector, but it will happen at the far detector. All the focus of this talk will be on the near detector. Why? Because it's very close to the source, and so there is a very large flux of neutrinos reaching to this large fiducial mass of the detector. And so the idea is using this to do the measurement of several rare processes in the neutrino sector that otherwise we wouldn't be able to study. So we need a very high beam luminosity plus a large fiducial mass to do this kind of a study. We want to specifically study neutrino-electron scattering and neutrino trident production at this detector. In this way, we can be sensitive to cross sections of the order of 10 to the minus 44 centimeters square, which is otherwise very difficult to study. And once we do that, we can test several standard model predictions, and then we can also use that to search for some beyond the standard model physics. And so in this way, perhaps we won't be able to directly search for some new physics, But with doing some precision measurements, we might be able to have some idea of where is the tail of new physics. Perhaps we can detect the whole body of the new physics, but at least we can have some estimation where it should be and what order it should be. So first, I will talk about neutrino Trident scattering at the near detector. I did this work together with people at Durham University, Peter Matthews and Silvia Pascoli, and also Renata Funchal from USP, as well as Juber Press from Fermilab. What is neutrino Trident scattering? That's the production of a charged lepton pair, a pair of charged leptons, from the scattering of a neutrino from the Coulomb field of a heavy nuclei or nucleon. So in this way, a neutrino hits a target, and it gives another neutrino, two charged leptons, and then the same nucleus or nuclei, but with just a different momentum. So it's a 2 to 4 process. This process has been measured before in 3 different experiments in CHARM2, CCFR, and NUTEV. All the 3 experiments, they happened in 1990s. They measured the cross-section of the Trident process, but as you see, the measurement is with a very large systematic uncertainty on the value of the cross-section. In principle, this alpha and beta here could be all different possible flavors, electron muon or tau. So it's not just nu mu going to nu mu plus mu minus. We can have all possible channels. We can have channels with tau neutrinos and tau charged leptons as well. But the channels with tau, we can't study them at DUNE, so I don't discuss them here. Otherwise, with just the final electron and muon channel, we can have these 6 possibilities. However, the only channel which has been measured so far is this first channel. At the 3 experiments I mentioned, CHARM, CCFR, and NUTEV, at the time, they weren't able to construct the electron vertices, so they were not able to measure any of these other channels, and they only studied the first channel. Why is it important to study a channel like this? Because once I show you the cross-section, this cross-section depends on the vector and axial couplings of neutrinos with the Z boson, which then they depend on the weak mixing angle. So by studying this channel, we can, for example, extract information on the value of the weak mixing angle. But it's very difficult to measure a channel like this because it's a very rare channel. How rare it is? If I compare the value of the cross-section of neutrino Trident production over liquid argon with respect to the charge current cross-section, depending on which channel it is, this cross-section could be between 5 to 3 orders of magnitude suppressed. So it's very difficult to observe a process like this at the neutrino experiments. The advantage of the near detectors is, however, we can overcome this with having a very large luminosity, having a very large flux of neutrinos, and overcome the smallness of the cross-section. I won't go into much detail about how we can calculate the cross-section. It's too much involved. However, let me just tell you that people knew since 1964 how to calculate the cross-section of a neutrino Trident production. Let me just tell you, it has a part which is the hadronic tensor, and it depends on the hadronic form factors, and it has a part which is the leptonic tensor, and it also depends on the center of mass energy of the total system. Depending on what's the energy of the neutrino, the incoming neutrino, the neutrino can interact with the whole nucleus. So in this way, we have a coherent regime, or it can only interact with the protons and neutrons of the system. And in this way, we have a diffractive regime. So depending on which regime we are, the form factors of this hadronic system are different, and the calculations are different. Let me just say one more thing about here, that we can go to the photon system, and we can separate the contributions to photon to the transversal and longitudinal parts. it will be clear in a moment why I emphasize on this. So in the last couple of years, there has been a lot of attention to studying neutrino trident production. These 4 papers are some of the most famous ones. It mainly started from this paper by Pospelov et al. That they mention how to use this neutrino trident production to search for new physics. However, a common thing in all these papers was that instead of the full calculation of the cross-section, they used an approximation, which is the equivalent photon approximation, which is widely used at QED. What is this approximation? It's saying instead of calculating the cross-section of the full system, we assume the photon is an on-shell photon. Then we calculate the cross-section of the photon neutrino system multiplied by the probability that these photons are virtual or off-shell and integrate over this probability. That is, if we put a cut over this photon propagator here, we only calculate the cross-section of this other part without considering any of these other hadronic difficulties. And then at the end, we just multiply by a probability of having this photon to be virtual. Let's see if it works or not. With respect to the full calculation, this EPA assumption means that we completely neglect the longitudinal contribution, and in the transversal contribution, we assume that the cross-section is on-shell. If we have a QED process, that means that this cross-section would be a function of the inverse of the center of mass energy. The center of mass energy is proportional to this Q square here. So having an on-shell photon means this Q square is 0. So a smaller values of Q square, which means a smaller values of this S hat, are making this cross-section larger and larger. So if we have an on-shell photon, it means that this will give the largest contribution to this cross-section, and it makes sense. The on-shell contribution is dominant over the off-shell contribution. However, we are at the Fermi limit for our calculation, and the cross-section is not proportional to the inverse of the center of mass energy, but it goes proportional to GF square times S hat. It means when we have a smaller and a smaller values of Q square and a smaller values of S hat, the cross-section is completely suppressed. So assuming that the photon is an on-shell photon is not a good assumption at all for the case we are studying. We can quantify how bad is this assumption that the equivalent photon approximation works or doesn't work. So we define this ratio. That's the ratio between the EPA assumption over the full calculation of the cross-section. This approximation would work if this ratio were of the order of 1. But we see that depending on which channel we have, the ratio could go very much different from 1. If we have a channel of nu mu going to nu mu plus nu minus, still for this big band, which depends on where we put a cut on this Q here, it could be still for some values of energy an approximation. But for the other channels, especially if we have a final electron, charged lepton, the approximation is never true. This is never close to 1, this blue band. The same happens for the diffractive regime. It's never of the order of 1. So this is saying we never should use this equivalent photon approximation for calculating the neutrino trident production. And we should use the full calculation, which is very complicated because it depends on all these form factors, but that's the only way for the neutrino trident production. Now that we have the cross-section, we calculate the cross-section, and we have the flux coming from the experiment, and we have all the information of the number of targets and efficiency and the lifetime of the experiment, so we can calculate the number of events. We first focus on the liquid argon experiments. We consider the 3 short baseline neutrino program at Fermilab, SBND, Macroboon, and Icarus. These are 3 different detectors, all at Fermilab. We consider the near detector of DUNE, and we also consider the new storm proposed experiment, which is Also, if it ever happens, it's supposed to have a liquid argon detector. And as you see, the number of events is orders of magnitude larger at the DUNE Near Detector. And that's why the focus of all our studies is on this experiment, not on the other ones. But why is it much larger? It's because of its flux. The flux of DUNE peaks at around 3 GeV, but it's a very wide range of flux. Although the peak is at 3 GeV, it decreases with energy very slowly. And it goes up to, I just showed that up to 15 GeV, but it could go up to 40 GeV. But the flux of, for example, the SPND detector, the other two detectors are very similar. It's just the normalization with respect to the distance. Their fluxes, they peak at much, much lower energy, and they completely stop. They become 0 at 3 GeV. The same is true about the flux of the Neutrino experiment. It has a completely different method for the production of neutrinos. But however, after a few GeV, we don't have any flux of neutrinos anymore. This is why for the cross section, it's very much suppressed before 3 GeV, and it only becomes dominant after 3 GeV. That's why it makes the DUNE Near Detector the dominant experiment here. However, since although the numbers here are very high compared to the other experiments, I should remind you that for the charge current and neutral current channels, we have something like 10 to the 8 events, something like 100 million events. So having a few thousand events compared to a few million events, a few hundreds of millions of events, it's still very much rare and very much suppressed. And we will only be able to measure a process like that if we know the background very well. And although if the signature is a pair of charged leptons seeing an electron and a muon, or 2 electrons, or a pair of mu plus mu minus at the same time, which is a very clean signature, there are still some particles that we could misidentify as these pair of charged leptons. A photon could be misidentified as an electron or a positron, or as a pair of electron-positron. Also, some of the pions, they could come to the detector before they decay. So we could confuse some pi plus, pi minus instead of some mu plus, mu minus. So in order to get rid of this background, we must be able to reach to a background rate, which is between 10 to the -5 or 10 to the -6 times the charge current rate, which is, as I've shown here, depending on which mode it is, up to 10 to the 8 events. Let me show here schematically what I mean. If, for example, for the channel of a pair of mu plus, mu minus, we don't consider any cuts on the background, then the total background we expect to see is this solid blue curve. However, the signal we expect to see for the Trident process is this dashed black curve. And as you see, if we don't put any cuts on the background, we won't be able to separate the signal from the background. However, we have studied different distributions of signal and background, and we have realized if we put a cut on the angle of this charged lepton with respect to the beam of the neutrino, another cut on the angle between the two charged leptons with respect to each other, and also another cut on the invariant mass of the system, then we can suppress the background to this purple box while we don't lose a lot of the signal. The signal would be still very much dominant. And in this way, the signal could be 1 order of magnitude larger than the background. So although we will have a very big background at this experiment, we will still be able to get rid of the background using all these possible cuts. We also studied this in several other experiments which they have finished data taking or they are still running. INGRID is one of the near detectors of the T2K experiment. We also consider the near detector of MINOS, NOVA, and also we consider the MINERVA detector, which is a multi-component detector, and it's supposed to study the cross-section of neutrino with several of these materials shown here. They have different baselines and different exposures and different fiducial masses with different ranges of energy. But still, in several of these detectors, we expect to see hundreds up to thousands of Trident events. So some of these experiments have already started looking for Trident events. Minerva people have contacted us that they've started their studies. So I hope before DUNE can happen, some of these other experiments can see some of the Trident properties. On top of the Trident, we can also study the neutrino-electron scattering. Despite the Trident case that the cross-section was very much complicated and very much involved, the neutrino-electron scattering has a very simple formula that we know it very well at the standard model. It's just this formula. It's an elastic scattering. It only depends on the energy of neutrino and energy of the recoiled electron, as well as these G1 and G2 couplings, which depending on which channel of neutrino we have, this G1 and G2 couplings depend differently on the value of the weak angle. So again, studying this cross-section, we can extract information over the value of the weak angle, as well as the values of this vector and axial couplings here, GB and GA. We expect to see of the order of 60,000 neutrino-electron events at the DUNE Near Detector. So it's almost one order of magnitude larger than the Trident events, but it's still 4 orders of magnitude smaller than the charge current events we expect to see at DUNE. How can we check the backgrounds here? The signature of a neutrino-electron scattering is that we just see a very forward-going electron. So with calculating the angle of this electron with respect to the beam, we can be sure if that's coming from a neutrino-electron scattering or some other source. The parameter experimentally people consider is this EE theta square. EE is the energy of the electron and theta is the angle with respect to the beam. We know that if we just look at the distribution of the neutrino-electron scattering, depending on what's the resolution of on the angle, which DUNE claims they can do as good as 1 degree, then the distribution of events is in a way that we can have a lot of the events on the smaller values of E theta square. So if we have a worse resolution, then we will have the tail moving to the right side of this curve. However, the background here, which are the main one is the charge current quasi-elastic, and also we have some misidentified pi 0. They have a flat distribution with respect to this parameter E theta square. So that with a cut over this parameter, we can get rid of most of the background in the right-hand side, while we don't lose a lot of the signal in the left-hand side. But that depends on the experiment with how good the resolution with respect to angle will be. So we want to use this neutrino-electron scattering as well as neutrino-trident production to extract information on the weak mixing angle. First, let me remind you that this cross-section, as I said, it depends on this G1 and G2 couplings here. If we consider the case of muon neutrinos, then as you see here, the cross-section, it depends on G1 square and G2 square. So if we change the sign of GV and GA, or if we just switch GV and GA with each other, the cross-section doesn't change. So we have a fourfold degeneracy here. It doesn't matter if we put GV or GA, GA or GV, or if we put them with the negative sign. However, if we consider the electron neutrino scattering on electron, because for this case, we also have the charge current, we have this extra 1 here, we lose half of this degeneracy, and we won't be degenerate anymore if we change the sign of these couplings. It will still be degenerate with respect to switching GV and GA, but it won't be, it will become a completely different cross-section if we change the signs. This is a very important information I'm going to use later. So first, we want to extract information on the axial vector and the axial and vector couplings. There have been several experiments which have already measured that. First, it was the CHARM experiment, which using a channel of neutrino scattering on electrons, it measured this. As you see, we have this fourfold degeneracy here. So what CHARM measures is all these four regions here. This is why, let me first tell you, the value of the PDG coming from several other non-neutrino experiments is given this star here. So the CHARM experiment can distinguish between all these other possible wrong answers with respect to this correct answer that we know is here. The Texono experiment has also measured this, but it's used a neutrino-electron electron antineutrino scattering with electron. And as I said, when it's an electron neutrino scattering, the degeneracy is half. So what Texono measures is these two regions here. It already got rid of half of the answers. The LSND also does a similar study. However, it's electron neutrino, not electron antineutrino scattering on electron. And because it's electron neutrino, the cross-section is slightly different. So instead of having two regions, it sees like one wide region here. But none of these experiments can ignore still this wrong part of the plane. And all of them still agree with both answers, although we know the correct answer should be here. So we want to use the DUNE experiment to solve this problem. And to do this, we use the idea of having a moving near detector. So what is this? In order to get rid of the systematic uncertainties at the DUNE detector, they assume they are planning to build a detector which they are on some rails so they can move perpendicular to the direction of the beam. So the beam comes from here, and they are planning to, instead of having a fixed detector like here, they are planning to move it perpendicular to the direction of the beam. Because in this respect, the backgrounds would be different in these locations, and they can, the systematic uncertainties would be different, and so they can get rid of the systematic uncertainties. So there will be the on-axis location, and then each time they move the near detector 6 meters more away from the perpendicular direction. Why is it useful for us? Because if we look at the ratio between the electron neutrino scattering over the muon neutrino scattering, at the location of the on-axis, when the distance is 0, this ratio is of the order of 0.1. However, when we go to more and more off-axis location, this ratio becomes larger and larger. That is because when we go to off-axis locations, we have several neutral mesons which contribute to the production of the electron neutrinos. And so we have a higher flux of the electron neutrinos. And it's important because we are using these electron neutrinos to get rid of half of their degeneracy. So that's what we do. First, we just use the on-axis one without using the prism idea to do the calculation. We get these green regions, which, as you see, they agree with CHARM. So it's because when we are at the on-axis, we mainly have only a flux of muon neutrinos. Then on top of that, when we use the idea of the DUNE prism, because we are having more and more electron neutrinos, we already break half of this degeneracy because of that. So if instead of the on-axis, we use DUNE prism, we only have these two darker solid regions. We already got rid of half of the degeneracy within one experiment, the same experiment. Now we can use the Trident cross-section to do the same measurement as well. The cross-section of the Trident one is a lot more involved, so it's difficult to show how the degeneracy is in there. But if we could assume that the masses of the charged leptons were 0, then we still could have a degeneracy changing GV to GA. But the truth is, we don't really have this degeneracy because the masses of the charged leptons aren't really 0 at the energy scale that we are considering. They are not negligible. If we use the on-axis location, then what we will see are these two purple regions. And you already see it's starting to move, even for the on-axis location, it's starting to move from this rank assumption. And so in this way, the only possibility of the right answer will be this possibility when we add Trident on top of the neutrino-electron scattering. Because what the Trident agrees from this other region is completely different with what all the other experiments agree. And it's only here that all the experiments, CHARM, Texono, LSND, and DUNE can agree. So using just the DUNE experiment, we can once and for all resolve all these degeneracies. And again, using that, we can extract the value of the mixing angle. We go to the MS bar scheme, which is the definition of the Wick angle is the ratio between G prime square over G square plus G prime square. And as you see, this depends on the energy scale that we are in. So in this sense, the Wick mixing angle runs, and depending on what's the value of this transferred momentum, the value of the Wick angle would be different. So there are several measurements for this parameter. The one coming from a neutrino experiment is from this NUTEF that they studied the neutrino nucleus scattering from this deep inelastic regime. However, as you see, the measurement of NUTEF is very much different from what the standard model predicts. It's more than 3 sigma deviation from the standard model value. There are many papers which try to explain why we have this anomaly here. But it's another proof that why it's important to measure this parameter using different neutrino experiments to see if we see the same discrepancy or not. So that's what we do with the DUNE experiment. First, we do the measurement using the on-axis. This is the value of the Wick angle we extract, and we find a 2% uncertainty on it. If we use the DUNE prism concept, the uncertainty is just slightly more, although the best fit value is the same. And although the uncertainty is worse, but the cost is solving the degeneracies in the vector and axial coupling plane, so it works to go for the DUNE prism concept. We can use all these scatterings to search for some new physics. We did this paper together with people at Durham, Sylvia, Peter, and Matthews, and Joubert and Renata from Fermilab, and Usti. We studied these prime models from a neutrinophilic Lagrangian. So we have the left-handed and right-handed leptons here. We add this Z prime with the coupling G prime. Depending on left-handed or right-handed fields we have these left-handed or right-handed charges here. If we also assume we have some right-handed neutrinos, then we have this extra term here. But for simplicity, we assume we don't care about the right-handed neutrinos, and we derivate them by putting this Qn here to 0. We focus on anomaly-free leptophilic extensions of the standard model. That is the possibilities of L alpha minus L beta, like for example, L mu minus L tau or Le minus L mu. And because we want it to be the anomaly-free, this fixes these couplings here. So with the anomaly-free conditions, we know the value of these couplings. Then what we don't know from this Lagrangian would be only this coupling and the mass of the Z prime. For the Trident scattering, then instead of just having this GV and this GA here, now it's also a function of this G prime and the mass of Z prime, as well as some kinematics, which depends on the momentum of the Z prime. As I said, the anomaly-free condition is going to fix these charges here. Now, if we just have the standard model case, then this distribution would be these gray regions. However, if we have like Z prime, we can have some excess of events depending on what's the value of the coupling or the value of the mass. We could have an excess of 3 times the standard model values. We can play the same game with the neutrino-electron scattering. Again, instead of just the weak angle, or here, depending on the channel, just a constant of plus or minus half. Now we have this dependence on the coupling G prime, as well as the kinetic energy of the electron. And again, instead of just these black curves, which are the standard model ones, we can have these blue curves, which are some excess of events, which depend on the value of the coupling and the mass of the Z prime. The difference between the dashed and solid curves here is what assumption we make on the resolution of the angle of the electron. So for the neutrino-electron scattering, we could also have that if we assume the Z prime can have some kinetic mixing with the standard model gauge bosons, then apart from these 2 couplings, we can have this other coupling induced by the kinetic mixing, which is now a function of this parameter epsilon here, apart from G prime and Z prime, which we had before. So although we have a model of L mu minus L tau, which doesn't couple to electrons, if we have this kinetic mixing, we can use neutrino-electron scattering to also study a model like this. So this kind of studies started from this paper from Pospelov. They used the neutrino trident production from CCFR. If we look at the plane of G prime over the mass of Z prime, the only studies at this range of the masses, the only study which had done before is this LHC study of a Z decaying to 4 mole. And as you see, it only comes as down as a few GeV. However, there hasn't been done any studies for lighter Z prime masses. What is this blue region? We know that we have this G-2 anomaly, G-2 of mole. There are several models which try to explain how we could have this anomaly. One of the possibilities is having L mu minus L tau model, and then we explain this anomaly by having this blue band here in the G prime over Z prime. So for these values of G prime and Z prime, we can explain this anomaly. Now, what Pospelov et al. Showed was using the CCFR experiment, we can already exclude a big part of this band. That is, all the values of the mass of Z prime larger than 400 MeV is already excluded, and it can't explain this G-2 anomaly. However, the values smaller than 400 GeV are still allowed, and also the couplings smaller than 10 to the minus 3 are still allowed. So what we did was doing the same study at DUNE and also adding a few other experiments here. For example, Babar, if we have the kinetic mixing, we can also use the Bruxino experiment, and we can also consider some cosmology bands. So first we focus on L mu minus L tau model. That is when our Z prime coupled to a muon, a charge muon, and a charge tau, but not 2 electrons. So in this way, we can use a channel of mu plus mu minus trident to extract information on that. And because of this kinetic mixing, we can also use the neutrino-electron scattering channel. The black curves are what we find from DUNE. As you see from the neutrino-electron scattering, in this case, we don't get much. What we get is already worse than what we have from CCFR. This gray region here is from CCFR. So it can slightly be better just in this region here where Broxino and CTFR, they cut each other. But if we consider the Trident case, which is this solid curve, we can already exclude the whole blue region, and we can exclude the whole region, which can explain the G-2 anomaly. We can also study the LE-LMU model, that is when RZ prime is coupling to an electron and a mu, but not to a tau. We already know that when we have a new physics sector with the charged electron, there are already several S-line constraints. So it's very, very difficult to build a viable new physics model which can couple to electron. And we can see that here. From Babar and from Texono and from beam dump experiments, already a very large part of the parameter space is excluded. What we can add from DUNE is using the Trident electron-electron channel because of the coupling with electron, and the Trident mu-mu channel because of the coupling with muon, as well as the neutrino-electron scattering. We get these different curves. And it's very difficult to make any of these curves comparable with the other experiments. The neutrino-electron scattering, which is the dominant one, it can be slightly better at this part of the parameter space, but it should you should note that all these experiments have already happened, and DUNE is going to happen perhaps in 10 to 20 years from now. So on this LE-LMU model, DUNE cannot do much. However, on this LMU-L tau model, DUNE can add a lot of information, and for example, it can completely exclude this G-2 favored region. So far, I just focus on a specific Z prime model. What happens if we have some completely independent and completely new physics independent model? So that is, if we don't focus on a specific model, but if we have a feeling some new physics should exist or not. I did this other paper with Adam Falkowski and Giovanni Cortona. So why do we use effective field theory? That's because in this way, in a completely systematic way, we can study several observables at different experiments, not just at the neutrino experiments, but on all high energy experiments, that they depend on very similar observables. And in this way, in a systematic way, we can compare these observables with each other. So we can, at low energy, we can use the neutrino experiments, and using this weak effective field theory, we can extract the information on the parameters here. Then, because this is a very systematic formalism, we can connect this weak effective field theory with the parameters of a much higher effective field theory. So if the new physics is at the energy much smaller than the Z boson mass, then our theory would be the weak effective field theory. However, if our new physics is at much above TeV scale, much above the mass of Z, like a few TeV or higher, then the theory is a Smith. And through this effective field theory formalism, depending on which energy regime we are, we can do the calculations, we can extract the information, and we can match all these constraints to each other. And then once we have some specific beyond standard model, we can translate the constraints on our effective field theory parameters to a specific model number 1, number 2, and etc. So what is the effective field theory? What is the Smith? It has the same particle content and the same symmetries as the standard model, but we just allow to have higher dimensional operators. We can have dimension 5 operator, which is the Weinberg operator, which explains the neutrino masses, or we can have dimension 6 operators, which, for example, is like having 4 fermion operators. So we don't care about the Weinberg operator because we don't care about neutrino masses here. We just focus on the dimension 6 parts. Then what happens is The vertices with the W and Z bosons, they change because of having these dimension 6 operators. Apart from that, now we can have several new four fermion operators. So let me organize a little bit better. If we have 4 lepton operators, then we can have several operators like this here. So that's the benefit of SMEFT, that if we are using this formalism, we don't care what's the new physics. There are a limited number of operators we have to consider. As I said, the couplings with W and Z also changed. In the standard model, we have these couplings depending on the weak angle, and now we have this delta GW and delta GZ that they are added to the Lagrangian. Now we have the same if we have a 2 lepton, 2 quark, just that with different 4 fermion operators and different dependence on this difference on the couplings. Now, when we go to low energy, which is the energy of our neutrino experiments, the Lagrangian is slightly different. And now this coupling that we measure here would be the value of the standard model with some deviation of the standard model value. So the idea is measuring these couplings, comparing with the standard model measurement, and then see how we can deviate from this standard model calculation. And then we can match the two calculations at the weak effective field theory, which is at our low energy, to the high energy, the SMEF theory. So when we measure these delta G's, then it will be a function of these parameters of the 4 fermion operators, as well as these delta G, Z, and W that I mentioned. The same for our 2 lepton, 2 quark operators with just a different dependence on the parameters. So we use neutrino-electron, neutrino-trident. This time we also use the charge current and neutral current interactions of neutrinos at the DUNE Near Detector. We can extract information on them. For this delta R nu E, when you use neutrino-electron scattering, there are these possibilities of the couplings that we can measure. This 2211 means the coupling with muon and electron. And we can find a constraint of the order of 10 to the minus 3 on this delta R. To compare with what other experiments like CHARM or CHARM2 or BNL have on these parameters, from the other experiments, we have this large green curve. But what we find from DUNE, if we assume a perfect experiment on this measurement, it would be this small orange dot. If we also assume some systematic uncertainty, then it becomes a wider range. However, it's still several orders of magnitude, several times better than the current constraint. We repeat the same exercise with the neutrino, with the charge current and neutral current. We look at the ratio between the neutral current over the charge current neutrino interactions, and we get a sensitivity of the order of 10 to the minus 4 on these parameters here. Again, from CHARM and coherent, what we had before was this green region. But from DUNE, we can get this small orange without systematic uncertainty and this larger curve with systematic uncertainty. We can do the same with Trident. With Trident, we don't find much because the number of events is a lot smaller, and we can constrain the same parameters, delta G2211, which is muon, electron, electron, and the sensitivity is 10 to the minus 2. From the neutrino-electron scattering, we had something of the order of 10 to the minus 4. So the same, so as I said, the advantage of using this effective field theory formalism to extract information on new physics is the same parameters can appear at several non-oscillation experiments. For example, the same electron coupling or muon coupling can appear at the parity violating molar experiment, which they measure this GAV-EE coupling. And so we can use the same constraint we find from here and compare with what we can get from the neutrino experiments. there are also several experiments that they are only designed to measure the value of the weak angle. These are the atomic parity violation experiments that some of them are already happening, some of them will happen in the next few years. So we can also use these atomic parity violation experiments to extract information on these electron quark couplings. And then we can put all of this information on top of each other to see which experiment can do better. So these are some of the parameters, not all the effective filtering parameters, but the ones we can be mostly sensitive to them. The blue ones are the ones we already have information on them from the current experiments. None of the current experiments include a neutrino experiments. They are, however, for example, LHC or in principle, the collider experiments or atomic parity violation experiments, and so on, but without any neutrino experiments. Then the orange one is all these other future experiments that I mentioned, but again, without DUNE. So for example, the future atomic parity violation one, you see that for several of these parameters, the future ones, they won't do much different compared to the current constraint. But once we add DUNE on top of that, suddenly the uncertainty on them becomes a lot better. If we have a perfect experiment without much systematic uncertainty, then we have these red errors here. If we have some systematic uncertainty as well, then it's a slightly larger, but still much better than the current and future non-oscillation experiments. So I quantify some of the parameters here just to show the numbers, just to say that, for example, depending on what's the parameter, DUNE can do between 1 to 2 orders of magnitude better on these measurements compared to the current experiments. Just to conclude, because I'm out of time, I studied several different neutrino interaction processes with a special focus at the DUNE experiment. I studied the neutrino trident and neutrino-electron scattering. We studied the standard model processes and got some information over the weak mixing angle, as well as the vector and axial couplings of neutrinos. And then we used the DUNE Near Detector to show that we can measure the weak mixing angle with better than 2% precision. Then we used all these interactions to study some specific Z prime models using the DUNE experiment. And we showed that DUNE will be able to completely exclude the G-2 motivated parameter space. And finally, I used DUNE to show that we can study in a model-independent way several new physics parameters using the DUNE experiment, which can be much better compared to the current constraints on them. Thanks for your attention.
Thank you very much. Any questions? Okay. We have one question, which I think it's someone whose microphone isn't working. I didn't understand very well when you said that the muon mass vanishes. What happens there?
Oh, it doesn't. It doesn't. No. So what I was saying was that if we could assume that it vanishes, not that it vanishes, compared to the energy of neutrino, we neglect the mass of muon, then we could have that degeneracy. But we know it doesn't happen, so we don't have that degeneracy. If we were in a regime, in a scale that, for example, the energy would be, I don't know, 1 TeV, and the mass is 100 MeV, then we could neglect the mass, but we can't neglect the mass here. By the way, the Q square here is a few hundreds of MeV, so we can neglect the masses.
I have a question that was sort of, I mean, one crucial thing that you don't scatter neutrinos of protons, you always scatter neutrinos of nuclei, right?
No, we do. That diffractive regime is when we scatter on proton and neutron. I didn't, yeah.
Is,
Yeah. So The numbers I show here, the first line is always when, sorry, I forgot to mention, when we scatter from nucleus. The second line is when we scatter from proton and neutron.
Well, I mean, the reason I was asking, just to, what you call the hadron tensors is sort of the quark wave functions inside the hadron.
Yeah.
They vary a lot when the hadron, when the proton is inside is by itself, versus whether it's inside the nucleus.
Oh, that's completely.
Which is okay, because people do measure this. You have deep inelastic scattering. However, it turns out, this is what's known as the proton spin puzzle. It turns out that how the spin is distributed inside the proton is actually also kind of a mess. We don't know. Roughly 30% is in the quarks, and the rest is in gluons, gluon extended configurations, and so on and so forth. I mean, this is sort of experimental data. And it turns out that there is absolutely zero experimental data on how that changes if the proton is inside the nucleus versus if it's inside versus it's isolated. There is zero theory and zero experiment. I mean, it's a complete no man's land, and this is one of the reasons why ERIC will be constructed, because it will be the first time that you'll have deep inelastic scattering with polarized nuclei as well as polarized protons. Does this worry you guys or not? Or is this a non-issue?
So,
because I'm polarized, so I would maybe it's a non-issue.
No, it's not such a big issue here, because so all the uncertainties goes on the form factors here. So yeah, there are some uncertainties on them, but so this goes into how well we can measure the scattering of neutrinos on argons, because we need all the form factors of argon here. And there are a lot of experiments which are already trying to study that. Not only this experiments at Fermilab, but also there's the JLab electron scattering experiment, which they are trying to measure that. So we put all of that in the shoulders of the experimentalists. This is the best we could do as theorists.
I mean, the point is that the form factor of the quark with the spin in the direction of, say, the proton spin or the nuclear spin is different from the form factor of the quark, which is pointing the other way.
Right.
This difference is also different between protons and nucleons, and no one knows this difference. And chances are it's pretty big because of Murphy's law. This is QCD. Everything that goes wrong will go wrong.
That's right.
And neutrinos only coupled to like the left-hand part, right? I mean, the weak interaction is chiral. So I don't know. I mean, I would be woken up about this at night.
That probably I'm not worried because I'm not a QCD person.
Okay. Okay. Any more questions? You can also write, you can say them, I'll unmute you, or you unmute yourselves, or you can write them and I'll say. If not, thank you very much. Thank you very, very much. And I'll stop recording.